Hello everybody. This is the notes for section 6.2 for Algebra 2 Trig. Gonna go freestyle a little bit here with this section. So we're talking about exponential functions. So looking at something like f of x equal to. Now, we've got two different types of exponential functions. We got exponential growth, exponential decay. Just like we talked about in the first section. So for the function, exponential growth, we're going to be looking at something like 2 to the power of x. Okay? The key thing to make it exponential is that the variable is the exponent. That's the only kind of function that has a variable as an exponent, or exponential functions. So, exponential growth, other examples, 3 times 1.5 to the power of x plus 7. All right, something like this. This could be function g of x. The key thing that makes an exponential growth equation, exponential growth, well, first off, it's got to be the variable as the exponent, but also your base. Okay, if we look at a generic exponential equation, the base, that's the number that you're raising to the power of x. For exponential growth, the base has got to be greater than 1. Okay? The whole idea of exponential functions is you're repeatedly multiplying by that value of b. If it's going to grow, that value of b has got to be more than 1. Similar idea for exponential decay. For an exponential decay function, your base is going to be a fraction. So like 1/2 to the power of x. We could have times 3 plus 7. But for exponential decay, the base has got to be greater than 0, but less than 1. Okay, it can't be equal to 1, otherwise you just multiply by 1 and you're not changing the value, so it just becomes a constant. Can't be 0 because you multiply by 0 and then the function's done. All right, so some other things to deal with for this stuff is, actually I can go back to this, transformations. This plus 7 in both these equations, those are shift up. These 3's right here, they are scale factor changes, and so what that's really going to do is just either change how fast the object goes up. It kind of looks like a shift up in certain spots, but it's just a scale factor change. So all the same rules that we have for transformations that we've done with all the other functions, they still apply. Adding and subtracting are shifts, depending on where you add or subtract. Those are your shifts up or down. You could have a function like this, x minus 2 as an exponent. Because you're subtracting 2 from x, that's a shift to the right. If we did this plus 3 right there, because you're adding 3 to the x, that would be a shift to the left, 3 units. Okay, so same rules as before. Now, I should also talk about what the graphs look like. For exponential growth, as you read left to right, the graph comes along here, just the most basic ones, and goes up real fast. So it's kind of like a horizontal asymptote in the negative x direction, but the graph increases very fast as you get to positive x values. For the exponential decay, the graph of that is basically just kind of the reflection over that y-axis. This is an exponential decay graph, or a standard looking version of an exponential decay graph. All right, so you got some transformations. Domains and ranges is all real values. There's nothing you can't take a base to a power of. The other thing is this idea called compound interest. Now, I believe you've seen something similar to this, probably in Algebra 1. Maybe not. But you have this equation, p times 1 plus r over n to the power of nt. All right, compound interest. The whole idea of this is, the easiest and simplest example is banking. You put money into a savings account. it earns some interest. All right, so you put $500 into a savings account. The bank pays you for that money. They just pay you an interest. It's it's usually like 1 or 2% per year. So something tiny, but they pay you for that. And so at the end of the year, that $500 that's been sitting there, they pay you a percentage of that money that you have with them. And they put that into your account. So now your account is worth more. Well, for the next time frame, like usually a year, that money that's in there, so if it's $500 and you earned 1%, now you have $505. Well, that $505 for the next year, that earns interest. So you're earning interest on top of interest. That is called compound interest. And it works in all kinds of different situations, but the banking idea is the most straightforward one, simplest for everybody to kind of grasp. So to figure out how much interest you have earned and how much the account is worth, we have this equation. So now, all these letters, the A value, that's your final amount. The P value, it's usually called the principal. I don't know if I'm spelling the principal like the school principal, or it might be an LE, I think, for this case. Anyway, principal. It's your starting amount. The value of R is the rate, like the percentage rate, but it's as a decimal. So if it's 5%, you would put in 0.05 for R. N, excuse me, N is the number of times compounded. So a lot of times what happens is, if any of you have a bank account, you get a bank statement every month. And so your bank will pay you an interest for that month. And so you've earned a little bit of interest for the month. It gets put into your account. The next month you have a little bit more money, so they pay for that. So you're earning interest on interest every month. So it's a number of times you're compounding, usually monthly, so N would be 12. Sometimes it's quarterly, so N would be 4. Could be weekly, so N would be 52. You get the idea. T is, it's time. Typically, it's years. It certainly doesn't have to be. Typically, it is. So a time frame. All right. So let's do one basic example. So the questions are kind of general. It says find the final amount of $500 invested for 8 years, and at 7%, and we'll go compounded monthly. All right, so want to know how much this account is going to be worth after the 8 years. So amount equals the principal times 1 plus. The 1 is representing 100%. If you're earning interest, this is a growth. So 100% plus, what is your percentage rate per month? So we take our rate, R, 0.07 as a decimal, divided by the number of times you're compounding, so monthly is 12. That whole parenthesis is raised to the power of N times T, number of times you're compounding over 8 years. So if it's 8 years and you're compounding every month, you got 12 times 8 number of compounds. And so this is the problem. Let me get out the calculator to figure out the answer. But once you've got the numbers plugged in, it really is just order of operations. So I start with the parenthesis, like you should. You got 1 plus 0.07 divided by 12. You get 1.0058 and a bunch of 3's. Raise that to the power of 12 times 8. You get 1.7478, blah, 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 times 500. which is $873.91. Okay, not a lot of money. That percentage is actually very high. I would switch banks to get to that kind of percentage, or at least start an account there. But this is the idea of compounded interest. All right, and that is essentially it. So, have a good day.